At the end of the previous video, we were looking at the phenomenon of attraction and repulsion that occurs between two charged objects, and I mentioned that it's described by Coulomb's law. So we'll go through that in a bit more detail now. So basically, just to start off with, imagine we have a charge here, we'll call that charge Q1, and another charge over here, charge Q2. And the other quantity that we're interested in is the distance between them, and we're going to denote that with the letter R. The reason why we use R is that distance, if you imagine it could be anywhere on a circle of the same distance, so it's a radius, but don't be confused by R. R is just the distance. To describe Coulomb's law, we're going to look at the quantities that affect the force between two charges. Now, the two charges that we're going to be dealing with, we're going to consider them to be point charges. And by point charges, we're basically saying that the distance between the charges is significantly large compared to the size of the object itself. So in this situation, we're saying that these charges are very small, the distance between them is very large. So the first thing to identify is that force is directly proportional to the product of the charges. Another way to think of that is that the force is going to increase regardless of which of the charges increases in size. So easiest just to identify that it's to do with both of the charges, so looking at the product of the charges. And if we were to write that in a mathematical form, what we would write is that F is proportional to Q1, Q2, so the product of those two charges. The second thing then is that it is inversely proportional. So that means then as one increases, the other is going to decrease, and it's inversely proportional to the square of the distance between the two charges. And this is another example of an inverse square law. Fairly common in physics to come across inverse square laws. And the notation for that one is that F is proportional to 1 on R squared. The final thing, so three key things about Coulomb's law. The final thing is that it's attractive for opposite charges. And so this is something that we've already seen. And it's repulsive for like charges. We'll come back to that towards the end, once we've gone through the mathematical formula for this, and we'll talk about how it is that we can get this idea of attraction and repulsion out of the equation itself. So if we combine those relationships, then we can identify that the force of attraction or repulsion is going to be given by the equation K, Q1, Q2 on R squared. So you can see we have the Q1, Q2, so proportional to the product of those charges, inversely proportional to the square of the distance between them. The value K then is the constant of proportionality that basically links all of these quantities together. So just to notate all of these quantities now, F is the electrostatic force between the charges, and when we're dealing with force, we know that that's measured in newtons. Q1 and Q2 are the charges, and the charges would be measured in coulombs, as we saw in the last video. R is the distance between the charges, and when we're talking about objects, it's really the distance between the centres of the objects. So when we're talking distance between, just keep in mind that it's always going to be between the centres, but I'm just going to write the distance between the charges, and that's in metres. And K is known as Coulomb's constant. And we need to talk a little bit more about Coulomb's constant. It's a bit of a slightly annoying one, really. It has a value that you can look up in the data booklet. So that's 8.99 by 10 to the power of 9 Newton meters squared per Coulomb squared. So again, that's a value that's given to you in the data booklet. The value of K itself, as I said, it's a constant of proportionality, but it depends on the substance that you're dealing with. So it's not just a value that comes out of nowhere. It depends on the substance, and it's actually given by a particular equation. Usually I'll go through and explain where the equation comes from, but we're just going to notate it here because it's not something we need to spend a lot of time on. But for a vacuum, the value of K is equal to 1 over 4 pi epsilon naught. So that is the equation that we need to be aware of, and you're probably looking at that and thinking, well, hang on, what's epsilon naught? That value is known as the permittivity of free space. Now, when you're looking at that, probably doesn't seem to make too much sense. Those words don't really seem to mean anything. The word permittivity, basically it relates to how easily it is for electric forces to be transmitted through a substance. Free space is just an old term for a vacuum. So when we're looking at this idea of K, Coulomb's constant, it really relates to the substance that you're dealing with. We're generally going to be dealing with free space, or we'll be dealing with sort of just in air, and the value for air is pretty much the same as it is for free space. That value of the permittivity of free space is 8.85 by 10 to the negative 12 Coulomb squared per Newton per meter squared. And again, that's another value that you can look up in the data booklet. To put it into context, as I said, the permittivity of free space is how easily electric forces are transmitted through a vacuum. Just as a bit of a reference point, we can have a look at the values of some fairly common substances. I'm not going to list out too many here, just go through three. The first one, if we looked at the permittivity of paper, the value for that is 3.4 by 10 to the negative 11, so you can see it's a bit higher than what it is for a vacuum. So you can straight away identify here that the higher the value of the permittivity, the harder it will be for electric forces to be transmitted through paper compared to a vacuum. For rubber, it's 6.2 by 10 to the negative 11, so again a bit higher than paper. And the last one that we'll jot down here is water, and probably doesn't surprise you that for water it's even higher again. It's 7.8 by 10 to the negative 10. So it's not just a little bit higher, it's actually a factor of 10 higher. So there's some values for permittivity of other substances, and you can identify there that for higher epsilon values, so for higher epsilon, that's going to mean that K will decrease, and if K is lower, the force will be smaller. So if the charges are the same, the distances are the same, but you've got a different substance, the higher the permittivity, the weaker the force will be between them. Now, I want to come back to the last thing I mentioned about attraction and repulsion. If you think about that equation, F is equal to K Q1 Q2 on R squared, if we have Q1 and Q2 having the same sign, that means the product of those two will always be positive. So Q1 and Q2, if they're both positive, the product of Q1 and Q2 is positive. If Q1 and Q2 are both negative, then the product of Q1 and Q2 will be positive. So that means that F will also be positive. And if we've got a positive value, what we can then interpret that to mean is that it's repulsion, because we know that same signs mean repulsion. So if the value of the force is positive, then we know that it's repulsion. Similarly, when Q1, well, not similarly, in the opposite sense, when Q1 and Q2 have opposite signs, so if one of them is positive and one of them is negative, the product of Q1 and Q2 will be negative, so F is going to be negative, and so that's going to mean that it is an attraction. Now be careful here because this is only dealing with the force itself. So if we have two charges positioned at certain distance apart and they're both positive, repulsion on the charge on the right means that it's to the right, but repulsion on the charge to the left means that it's to the left. So the positive means the direction of the force compared to the other charge. It doesn't mean that we can say that to the right is positive. That's not going to work in this particular scenario. You have to be careful about the direction of the force, indicating that repulsion means to the right on charge Q2 and means to the left on charge Q1. Notice also that the magnitude of the force will be the same on each of those charges. So the value of F is about the quantity of the charges multiplied together and the distance between them. And the direction is then whether the charges are being repelled or whether the charges are attracting.